Welcome to Related Rates Part 2. If you're watching this before you watch Part 1, you probably want to watch Part 1. It helps out with some of the analogy that I'm about to be using. So let's get to it here. An airplane is flying on a flight path that will take it directly over a radar tracking station. Let's zoom in just a little bit here. Or a tracking station as shown in our figure over here. The distance S, which is right here, this is an X up here. I think you can see that's a 6 miles there. The distance S is decreasing at a rate of 400 miles per hour. So, but not all the time. At 400 miles per hour when S is 10. That's just at one instant because S is changing. This plane is traveling this way. That's the movie. And as the plane gets closer and closer to here, S is getting smaller and smaller. Imagine when the plane was out here, S would be much bigger. So that's part of our snapshot. In our snapshot, we've got S is 10. When S is 10, S is decreasing. ds at a rate of ds dt equals negative 400. What is the speed of the plane? Okay, so this is kind of our movie right there. So part of our snapshot could be what's going on right here. At some point, this is 6, this is 10. This is part of the snapshot as well. And this distance would be 8 right up here. X would actually be 8 at that snapshot. Okay, that's a 3, 4, 5. So X is actually 8. So we've got X and S. Let's see what we want. What's the speed of the plane? Well, the speed of the plane would be the rate of change of X. What we want is dx dt at that instant. There's the things we know snapshot-wise. I believe that's all of them. There's what we want to know. We want to know dx dt when S is 10. Oh, by the way, that makes X be 8 for that instant. But ds dt is also negative 400 at that. It's shrinking. Okay, so how do we've got this X and we've got this S and we've got this 6 that we know something about. When you get triangles, which is frequently, sometimes you're going to be interested in angle measures, but there's nothing about this that makes me think we want angle measures. Because as this plane flies, the right angle stays the same, but this angle would change, this angle would get smaller as X approaches. Sometimes you're interested in areas. So you might be using trigonometry with angles, you might be using an area formula. But in this case, X and S and the 6 that we know, there's a nice Pythagorean relationship. So let's jot that one down. We've got 6 squared plus X squared equals S squared. And why am I not putting 8 and 10 in? Because those are changing all the time. When do I put 8 and 10 in? If you watched the last video, that was a point of emphasis. Only after we take a derivative. So we get 36 plus X squared is S squared. Now let's take derivative with respect to time. Derivative 36 is 0. This is 2x dx dt equals 2s ds dt. The 2's can cancel on both sides. And now, what are we trying to solve for? Or maybe we've taken our snapshot, let's put our snapshot values in. Well, X may be replaced by 8. dx dt is what we're looking for. S may be replaced by 10. ds dt may be replaced by negative 400, and we've got it. So that is dx dt equals negative 4,000 divided by 8 or negative 500. Now it asks for the speed of the plane. X is getting smaller and smaller at a rate of 500 miles per hour. Therefore, the speed of the plane is 500 miles per hour. You need to be careful on the when do we want to interpret things as a negative, as a positive. It's based on what the equation is. Or what the question is. If it said how fast is the distance to straight above the satellite tower, how fast is that changing? It would be negative. But how fast is the plane moving? 500 is positive. Okay, and number 5, another triangle problem, as you can see. And even without reading it, I got a pretty good feel what's going on. This plane, this rocket is going up, I suspect. So this distance is going to change. This distance right here, tracking that, is going to change. This angle theta is going to get bigger as that rocket ship goes up. This angle would in fact get smaller as the rocket ship goes way up. It's going to get smaller. But this distance is going to change, and they're calling this one S right here. You'll find out S is used for position an awful lot in physics. And oh, by the way, they threw this here, and that's just a hint that probably I would have rather them not given us here in this diagram. So I imagine they're going to be talking about theta in this. Find the rate of change in the angle of elevation from the camera at 10 seconds after liftoff. The movie is the whole thing playing this rocket going up into space. The snapshot is when the rocket's has been up in space, or the snapshot is taken 10 seconds after liftoff. So here's our snapshot right here. T equals 10. And we're supposed to find the rate of change of the angle. So we want d theta dt. We want to know it. What else do we know? Well, we got some reading to do. Television camera at ground level is filming the liftoff of a rocket that's rising vertically, and its position is S equals 50t squared. Well, S equals 50t squared after 10 seconds. S equals 50 times 10 squared would be S equals 5,000. So I'm just going to draw what's happening here at our snapshot. This is part of snapshot as well. This would be 5,000. This would be 2,000. I got a little annoyance here in front of me. Excuse me. This would be 2,000, and since this is a right angle, we can figure out this. This would be square root of 2,000 squared plus 5,000 squared. So we got all of that stuff going on right there. That's part of snapshot as well over here. And this 2,000 stays constant all the time. This happens when t equals 10 as well. Okay, so this is a big hint, but because we want to talk about theta, we can use trigonometry because we've got the opposite, we've got the adjacent, we've got the hypotenuse, but it does make sense to use opposite and adjacent at this time just because they're a little bit cleaner numbers. So they've said, oh, by the way, tangent of theta is S on 2,000. So tangent of theta is S on 2,000, and I want to end up finding d theta dt. So d theta dt, if I take the derivative of both sides, I get the derivative of tangent, and I suspect you may have to go back to your derivative rules for this one, but that is secant squared of theta, but with respect to t, treat the baby, d theta dt equals 1 on 2,000 ds dt when we take the derivative of the right side with respect to t. So I want to get d theta dt alone, and I could do that. I could do that by dividing both sides by secant squared, but hopefully you recall that would be the same as multiplying both sides. Did I say cosine? Hopefully I said secant squared. Multiplying both sides by cosine squared times 1 on 2,000 ds dt. And now, what do I know? Oh, I've got, I don't know theta yet, but I've got a ds dt right here. Maybe I should take the derivative of this thing as well. Watch this. ds dt equals 2 times 50, 100 t dt dt, but those cancel. Oh, ds dt may be replaced with 100t. So d theta dt equals, I'm going to save this cosine squared for just a minute. 1 on 2,000 ds dt is always 100 t times cosine squared of theta. Okay, well that's great, but I need to know what t is. Oh, t is 10. Well, that's great, but I need to know what cosine is. Cosine is x on r adjacent on hypotenuse. I've got it all. It's a big mess, but I've got it all. d theta dt, simplify this, that would be t on 20. T is 10. 10 on 20. Cosine squared theta, or d theta dt equals 1/2 cosine squared is 2,000 on that. And this thing might actually simplify out pretty nicely, but I'm going to go ahead and go to calculator right now. I'm going to be really careful with my calculator here. So I got 0.5 times quantity. Let's fraction this guy. I've got 2,000 on square root of 2,000 squared plus 5,000 squared. Hopefully this thing's still recording. I had a screen black out there for a second, and I need to square that. And I end up with approximately 0.069. What are we dealing in here? This is d theta dt, so that's how fast this angle is changing. When you use this process to find angles, the answer you're going to get is going to be in radians. So that is radians per, where are we at here? The camera is changing angle of elevation, 10 seconds per second. If you want that in degrees, times 180, so we're changing at 12.414 degrees per second. So a little bit more going on when you got to find the angles, but again, it's just kind of to illustrate puzzle pieces going on here. And you're going to get some practice with these, and along the way I'm going to fill in some hints. As I did mention, that if you get some things like you'll see here in number 6, that you've got a volume problem, you've got a cone problem, conical cone problem, gives you the formula for the volume that you're going to need. Must be another cone problem. So I'm going to give some formulas if I believe you should need those. For finding derivatives of things like tangent or secant, you can go back and refer to the worksheet that I gave you, or actually the note sheet that I gave you on different types of derivatives. So there you have it, and I'll get this broken down into a couple different assignments. I definitely expect people to be networking with one another on these, but have fun with them. Keep in mind, the biggest point I want to make on this is we're going to have to take a derivative to find the rate of change of the elevation of the camera, d theta dt. We're going to have to take a derivative with theta in it. Do not put the snapshot items in until after you take the derivative. Don't say, well, t's just always 10. Wait until after you've taken the derivative for that. Otherwise, you're going to get yourself in trouble. Okay, let me know what I can help with.